Ready.
Happy astronomy! Woo! Hi, I'm Jody. Welcome to Astronomy this evening with our lovely Dr. Lucas Cook. Just to, if you hadn't had a chance to look at a little bit about Lewis's background, he graduated from WVU in 1973 with a doctorate and practiced family medicine in Fayetteville for 42 years. Now, in his copious free time, he had all kinds of other things he thought it would be interesting to do. So in addition to his works, he also has a PhD in paleontology and geology from WVU as well. He also has a master's degree in physical anthropology from the University College London and completed graduate work in astronomy. This stuff. Now, something else that's really exciting that Lewis is involved in. He's an early member of an international medical geology field, teaching this internationally and as a specialty. So it's a real cutting edge, moving the needle that next level. But for me, I've known Lewis as a member of our community for many years, but have gotten to know him through the Master Naturalist program, and it has been so amazing to see this man and explore with him, and such a great breadth of knowledge and so many things. I'm particularly excited about tonight because I love stars, but he's the guy who can help me further my ventures and the starry night and beyond. Carl Sagan once said, somewhere something incredible is waiting to be known. Lewis is going to help us get there tonight. Please welcome Dr. Lewis Cook.
Of course, you guys know people that do too many things don't do any of them well.
Yeah, right.
So, limited expert in various fields.
Well, there's the other side of that, where folks say, if you want something done, give it to someone who's busy.
Well, speaking of busy, I've been given the task of teaching astronomy for beginners. Now, and I purposely put it in that font because it's a little difficult to interpret. It's difficult to, it's like giving you lessons in being a physician in an hour. Well, teaching you about astronomy in an hour is a challenging task. But we'll give her a shot. Right. How many in here are already astronomers at one level or another?
You have to qualify
I
that.
like the stars.
Yeah,
Well, I
looked
mean,
at the
I like
stars.
the stars.
Do you go out and look at the sky and you know about what you're looking at very well?
A little bit.
Very.
So varying degrees about it. Everybody knows some astronomy. So some of you that know more are going to be more bored with some of this, and some of you that know less, and the rest of you just won't even care. So it'll be we'll take a shot at this. So when you go out and look at the sky, not tonight, but if there's no clouds in the sky, and you look up, this is pretty much what you see, or a variation on this. And most people look at this and they go, they just kind of intuitively call these points that they see up there stars. Well, it's a long ways from what that is, as some of you know. There's a lot of different things that you're looking at that show up that way. So what we're going to do tonight is to try to organize it so when you look at the sky that you have a better feeling about what you're looking at when you look at the sky. So the way we're going to do that is we're going to do a kind of a brief review of the organization of the universe. Believe me, any review at all that could be done in a week would be a brief review. It won't really, it is. But this will give you a way that we generally organize it. We're going to talk about the major objects seen in the sky, how it all fits together, how you label those. There's a lot of ways we label these objects. There's millions of objects. They all don't have names, but they all have designations one way or another. We're going to talk a little bit about sky charts, and I also want you to kind of see what you actually see through a telescope. Although we won't have a telescope set up, I want to show you some things that you would see if we did, and what you actually see compared to what you think you ought to see. Because there's a big difference. And then we'll talk about some of these references that you can start with. What I brought is primarily what you might buy to get started in astronomy. I mean, I've got literally, bookshelves, just hundreds of books on astronomy. Most of those are really, each book has a special area, but these are general getting started books. We'll talk about that. Okay, so this is a little better look, a little bit more what you're used to. Now, these lines that you see on there that line up these different bodies in the sky are arbitrarily put there to mark out constellations. We'll talk more about constellations and what they mean, but those are just simply artificially hooks these together in what people in the past have looked up at the sky and pictures that what they thought that those shapes represented one way or another. We still use those terms today, but you also have to recognize that what one culture called shape of stars, another culture wouldn't see the same shape or use the same name. So there are different cultures calling different constellations in the sky. I mean, they didn't have these things a long time ago, or those things, or movies. Their entertainment is going out and looking at the sky. So they have a lot of time to look up there and use their imagination. Some of the things we can see are actually going to be stars. Some of those things that you see scattered around that don't have any names on them are stars. Constellations we've talked about, planets, moons. You can actually see moons up there with the naked eye. Asteroids, meteors, comets, satellites, space station, airplanes. You can see all those with the naked eye. Okay? We'll talk about it. I want you to not forget that you're actually seeing the same objects are there during the day. Some people think that during the day they just aren't there. It's not that they're not there, but you can't see them because our atmosphere, clouds, and light blocks it out. But they're still there. And actually, I'm sure all of you have looked up at the sky during the day and seen the moon. And some people are even puzzled by that. I've had people call me and say, I looked at that, I can see the moon. How can you do that? You can see Venus, it's the evening star. You'll see it coming up right in daylight. And of course, obviously, you can see the sun. And there's a lot of things out there that you just can't see. So where are we in space? The way we organize the different aspects of being in space, we'll just go from the center out, step by step. So, first of all, we're on the Earth. And I assume most people know where we are on the Earth. About right there, where the clouds are. And then, of course, our Earth is in a solar system, which is our all the other planets and the sun associated with it. And then there's what we call a solar interstellar neighborhood, which is some of the bodies around our solar system in our neighborhood. And then that's part of our Milky Way. This is where we are, where that red starts. This is where we are in the Milky Way. Then there's a local galactic group which has more than one galaxy. And there's a lot of local galactic groups around, but it just so happens we only have one other galaxy in our galactic group. Anybody know what it is?
Alpha Centauri.
Andromeda.
Alpha Centauri.
Andromeda.
That's that one right there, that spot. So we only have one. That's our closest next galaxy to us. And within our group, that's those two. Then we have the supercluster, which is a bigger group of other local galactic groups. And then we have our local supercluster. Now, the main reason I want you to think about this is to get away from this idea that things are just evenly divided and distributed all over the universe. They're not. They're in clusters. And each one of these areas are just one of these, and a whole bunch of those. And then the observable universe, of course, we're in the center of the observable universe because we can look in all directions the same distance. So we'll talk some about each one of those. Our neighborhood, of course, is our solar system with our sun. Our sun is a star, and we'll talk a little later on about what kind of star. It's an ordinary star. We don't have anything to brag about or be ashamed about with our sun. We're just ordinary, and I'll tell you why in a minute. And of course, you have at least the inner planets are shown here, and this is part of the asteroid belt. We'll talk about the asteroid belt. That is, Cetus is one of the asteroids in that belt. This is a little more detailed, so those of you who don't remember, I'm sure all of you heard this. We have eight planets with Mercury and Venus being inside of the Earth, and then Mars, Jupiter, Saturn, Uranus, and Neptune are gaseous planets, and they're much bigger. These are drawn to scale pretty much. Down here's little Pluto. Little Pluto used to be thought of as being our ninth planet, but we took that away when we started exploring this Kuiper belt and found out there were a whole bunch of things just like Pluto and that. Pluto was not a planet. It was never felt by astronomers to really be a planet. That was one of those board decisions made by a board that shouldn't have been making that kind of decision to start with. And everybody knew it didn't have the right kind of orbits and it didn't have the right kind of behavior to go along with the other planets. So that's not anything new, but they finally made it official a few years ago. That really wasn't the planet. So that's what happened with that. So this is our local interstellar neighborhood. It includes our solar system that we just looked at, plus a whole bunch of other bodies around. And we're starting to get into some of these. The reason I put these here is because a lot of these have these designations. Gliese 436. Gliese is just the person who set up a catalog of bodies in the sky and put numbers on them. And so that's what they name it that way. Or the Henry Draper catalog, these HD designations that you'll see. There's one here. Usually those are, a lot of these catalogs are just the catalog name plus a number. So there's a whole bunch of them. We'll talk about some more later on. But this is our local interstellar neighborhood, which just includes our local solar system plus those things that are close around it. And of course, going back to the Milky Way galaxy. Now, how do we know that the Milky Way galaxy looks like that? Did somebody go out there and take a picture of that? Did they see it in the telescope? Does anybody think that happened? Well, of course it didn't happen. There's no way we could have gotten far out enough to look back at our solar system. So we've made a decision about what our solar system looks like by the data that we've collected, by looking across the edge from here, across the edge and collecting data over the years. We're still collecting data. We still don't have it right. For example, I'll show you in a minute why this picture is not correct now. We think it really does have a different shape than we thought. By the way, when you look through the edge of that solar system from our perspective, what is it that we see and what do we call it? The Milky Way. Okay? That's what it is. Now, we don't see much Milky Way around here because we've got way too much light pollution. The enemy of astronomy is light pollution. And we just do not get to see the Milky Way very well. If on a really clear night, you'll see sun. But if you any of you that ever been out west, the Rockies or Wyoming or Arizona and some parts of Washington, even the bottom of the Grand Canyon, I could look up and see the Milky Way, how clear it was. So, so we don't see it very clearly, but that's what we're looking at. So, do we have our Milky Way galaxy, as I told you before? Our only other galaxy in our local galactic group is the Andromeda galaxy, and all those bodies of any significance between.
Lewis, I got a question. To be in our local, what is the farthest away star in our local galactic group in light year distance?
I don't know. And then the superclusters, like we talked about, these are just a whole bunch of clusters like that we just designated as our local supercluster, and we've named it the Virgo supercluster because it happens to be Virgos in that area. So they're just designated that way. And then, of course, this is where we are in the middle of what we can see of our universe. We'll talk a little bit about what we can see and why we can see it.
In the last couple slides, there's like a top and a bottom.
Yeah, that's not really.
Is that just how far we think we
It should
can
be a
see?
sphere, but they've made a cylinder out of
But
it.
is it based on how far we think we can see?
Yeah. We're gonna look at some images later on to show you why that's like that. But actually, it should be. It should be more of a sphere than a cylinder. How far can we see? Well, with the unaided eye, we can see 2.6 million light years. What's a light year? How does that relate to distance? A light year down here is the distance light can travel in a year. You know how fast light travels and how far it would travel in a year? That's 5.8 trillion miles that light can travel in a year. So when you say something's 1 light year away, you're saying that it's 5.8 trillion miles away. Now, one of the things that you've got to wrestle with in astronomy is dealing with the enormity of the numbers. It's like our national debt. It's just something I can't even, I can't deal with. I don't know what it means. And you're going to do that constantly with the numbers that we're in astronomy. By the way, that's 1 trillion, the number. Just so you can kind of see a number. We don't use the designation of trillion. Another way to look at it is just for light to get from our sun to our Earth at 93 million miles takes 8.3 minutes. 8.3 minutes. So what we're looking at when we look at the sun, or we have the light shine on us from the sun, happened 8.3 minutes ago. And that's the way it is on all these things that you see in the universe. When it says that something is 1 light year away, or 5.8 trillion miles, 1 light year away, what we see is what it looked like then. It's not what it looks like now. It takes that long for the light that we're seeing to get here for us to see. So that body that we see may be gone. It may have exploded and be gone by now, within that time frame that it took the light to get here. Everybody see that? Now with binoculars, you can increase how far you can see to 10 million light years. That's a big jump in what you can see just using binoculars. We're going to talk a little bit more about using binoculars. People don't use binoculars enough. They want to go for these big telescopes that they don't know how to use and get real frustrated with and pay a lot of money for. And, when you really ought to start with binoculars. If you use an 8-inch telescope, you can get back to 2 billion light years. 8-inch. My two larger telescopes I have a 11 inch and I've got a 14 inch. So every time you add an inch, you almost double the distance you can see that. But that sounds pretty impressive. But when you think about what you're looking at being so small and so far away, that even though you double what you see, you're going from something that may be that big to something that's that big. And spending thousands of dollars to do it. Okay. So I do a lot of planetary view. I like to look at the planets and the moon. I did projects on measuring things on the moon, and those kind of telescopes are sure make that a lot easier. But when you're looking up into the sky, you're not getting that kind of benefit. So, just as I said, you actually see what it looked like back in time, given the distance. We've already talked about all. So this is just to summarize this. These are the subdivisions of our solar system, layer by layer. Most people don't go through all this. Most people don't think about the Earth. They think about our solar system with all its planets and moons and things that we have in our solar system, which is enough to deal with. And then the next step is the Milky Way. We think about that. And then the next step is the rest of the universe. These intermediate things are not really sexy enough to be too concerned about. People don't sit around and talk about our local solar neighborhood. I mean, that's just, we know it exists. We just don't use all that terminology. Now this is the how far you can see back in time lesson. How many of you all are familiar with the Hubble Deep Field Image? Well, a lot of listening for a while. You don't get to hear so much now. Although the Hubble's failing, everybody know why the Hubble's failing? What is it about the Hubble that's failing? Huh?
It wasn't designed to last this long.
Well, but what is it that wasn't designed?
Energy source?
It's the gyroscope. There's 32 gyroscopes in the Hubble, and that's what stabilizes it and allows us to point it and focus, and we're just losing by the day. I think we're down to 4. I mean, there's still certain things that it can function for, but it's going to quit. But the people that were in charge, JPL, who was in charge of the time used on the Hubble Space Telescope, which was really intense for a long time, it kind of waned off for a while. And a couple of the people there said, well, let's see what we can see in these dark places in the sky by leaving the telescope on longer. There's 2 or 3 things that allow us to take pictures of things in the universe. One of them is the power of the telescope, the lenses in it that create the magnification. Another is what you've got between the telescope and what you're looking at. For example, that's why the Hubble telescope is much more successful in looking at things, is we got it out of our atmosphere, and we don't have our atmosphere to look through, like out there. Hubble doesn't have those days. No matter what you do, you've got a lot of atmospheric changes, moisture and clouds and light, pollution and everything to get through, so that really does it. The other thing, and the thing my biggest point is how much time you can keep that camera aperture open to gather the light from the object that you're trying to photograph. The longer you leave it open, the more light photons come from that object into that telescope and gather on that plate as a chain. So if you those of you who are into photography, if you you want to take an image and get a lot of detail, if it's still, you can hold that lens open for a while or delay the closure on the image, and then you can blow it up bigger and get a lot more detail. Well, the same thing's true in the sky. So their idea was, we'll pick a place in the sky, in the field of the Hubble telescope that's dark, that we can't see anything in. It's completely dark. There's no points of light, no stars, no anything. We'll point our telescope at that hole and leave it on for a week. And never done anything on it. Well, to their surprise, I mean, they thought they might see a few things, but this is what they ended up seeing. Now, in fact, the calculation is that they were actually getting light from objects that were 13.3 billion years. It took us that long. It took that long to reach. The age of the universe since the Big Bang is only 13.7. So what you're seeing here in this image are objects that existed in the sky 13.3 billion years ago. That's right after the Big Bang, relative. Yeah.
Is that true color?
No. Well, yes and no. We don't really see the color directly. A lot of times we see the spectrum that it falls on, and we calculate where it is. But we also see the colors, especially red, yellow, the things in our spectrum. Of course, we have all kinds of devices that measure all the rest of the spectrum as well. Microwave, X-ray, gamma ray. So we can calculate the spectrum and fill in some of these things that we really can't truly see colors at the moment. But you'll see there's an awful lot of red here, more red than you would expect. And we'll talk about the Doppler effect. For those of you who know about that already, I'll explain it to you in a minute. For those of you who don't. Yeah.
So you're actually seeing things that were 0.4 billion years after the Big Bang.
Yes.
And at the Big Bang, things started expanding.
Right.
So some of these things could be things that we see in other ways that were there then, but they're someplace else now.
No, that's where they look then. We don't know what they look like now, or even if they're there now.
Right.
But they could be somewhere else now. We could.
Well, could be. Most bodies in the sky who are solid bodies, especially suns do not last long. Our sun, we're halfway through the life of our sun, and it's going to explode and disintegrate. It's 4.6 billion years old. We've only got another 4.6 billion years, and we're toast. Okay.
Well,
So you need to plan on
we'll
that.
knock ourselves out long before the sun does.
So that's our ordinary sun. The other bigger suns, smaller suns, have different rates that they burn off their hydrogen and last longer. There's a lot of theory in
So probably a lot of these things no longer exist,
right.
but some of them might.
Right. And they could recycle. See, a planet blows, or a sun blows up, it turns into a cloud of dust. That dust gradually concentrates back down and forms a new galaxy.
And some of those things that look like galaxies, they probably are galaxies.
A lot of these things that we think we know today, we find out maybe later on. Maybe we don't know what we thought we did. About Ramses. Rumsfeld's. There are things we know, there are things we know we don't know, and there are things we don't know that we don't know. Okay?
Yeah.
That really applies to astronomy. But I'm just giving you the present thing. So here's, these are the different, at 5 billion years ago, this is what they saw 9 billion, then more than that. So you can see that it differs at different layers. We're talking about what you're talking about. WFC is the wide field camera. So let's go back to the bodies. Let's go back to the planets. Most of you all know a lot about planets. There's a lot said about it. These are good pictures of planets, and you can see the order again: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus. Between here is the asteroid belt. Uranus, you know, is turned sideways. We think it was hit by a body somewhere along the line. It was during the formation, or right after some big body came to our universe and hit it. Could have been a big asteroid. It could have been in lots of things. So it's turned on the side, and it turns this way rather than this way. There's a lot we can talk about each planet. It's really interesting. We just can't do that right now. There's a lot of moons in our solar system. These are just a sample. Of course, you know, Venus and Mercury do not have any moons. We have one. Mars has 2, Phobos, Deimos. They're just little irregular. They're not even very spherical. They're just kind of irregular bodies that kind of fly around. Very small. Jupiter actually has 63 moons. Now we know about the classic moons that were described by Galileo that we can actually see. And by the way, you can see all these moons with a set of binoculars very well. The binoculars that you bird watch with are much stronger than Galileo's telescope that he saw those moons. But the trick was that these moons, I'll show you another picture in a minute, were in different places at different times, and that's what made him think that they were rotating around Jupiter, which was against all thinking of the day. The thinking of the day, especially by the Catholic Church, was that the Earth was the center of the universe and everything rotated around the Earth. And there wasn't any such thing as anything rotating around anything else besides us. And of course, that's what got him in trouble when he kept insisting that he felt that was what's going on. Saturn has actually thousands of moons. These rings around Saturn have all kinds of bodies in them that form those rings, thousands and thousands. So each one of those technically is a moon. But you know, as far as named moons, we name about 62 of them. These are the biggest. Titan, of course, is one that most people know about. Uranus has 5 or 6 moons. Neptune has 3. We know, but most people know about 3. You know, Pluto has a moon around it, Charon. These are all relative size to the Earth here, so that gives you an idea how big those moons are relative to the size of the Earth. Like a good rule of thumb when you want to think about the size of the planets is you can see our moon is about 1/3 of the size of our Earth, and Mars is right in between those two. Mars is twice as big as the moon, falls right in size between the Earth and the moon. No, not exactly, just for some reference. Now, how about stars? Okay, now stars are actually burning. They're burning hydrogen, and they're fusing hydrogen into helium. And by that fusion process, they're generating energy and light. That's what all stars do. eventually that hydrogen is all converted, or mostly converted to helium. And what's keeping that sun expanded is all that energy. So once all that hydrogen is burned or nearly burned, that energy doesn't exist, so it starts shrinking down. And when it shrinks down, it'll eventually shrink down to a point where it's so intensely packed that it explodes. And that's what destroys the star. Now, if it's a big enough star, it'll turn into a red giant. Anybody know about Orion? The constellation Orion?
Yeah.
Okay. What's the alpha star, the bright star of Orion? Betelgeuse. What is it? A red giant. It's an exploded sun. And it won't be there long. I mean, it'll probably outlive us, but that's...
Lewis, I got a question. So I think we think of burning as being oxidation.
No, well, burning in a classic sense on the Earth, yes.
But so what is burning
fusion.
of hydrogen to helium?
It's fusion. It's like fusion that takes place in a nuclear weapon.
So that releases a huge amount of energy, and that's burning.
Well, it's not burning. It's just releases energy.
Okay, so we're calling that release burning.
Well, I shouldn't do that.
But it's releasing all this heat, and it looks like burning to us.
Well, it
Heat and light.
yeah, just
Okay.
like an atomic bomb going on for a hydrogen bomb. There's two kinds. There's fission and fusion. There's fusion's where that's the energy we keep trying to get so we can get free energy. And fission is where it's the other way. It's actually ejecting protons into other atoms and this chain reaction and stuff. So,
Okay.
but the things that goes on in the sun is fusion. So anyway, we classify this by this HR diagram, the Hertzsprung-Russell diagram. Two people have described this, so we could just get it in. Our sun is a yellow star. There's all the colors are one of the things that we talk about with stars. We call it a yellow star, a red star, a white star, a blue star. You can actually see those colors. By the way, that's the way the Milky Way ought to look. And then we do things like the luminosity is the brightness of the star. Okay? And the temperature is the heat of the star. So Betelgeuse is right there. So it's a really big star. But it's relatively cool. It's just really big. And we talk about the spectral classification of stars. So when somebody tells you that it's an F star or a G star, you know what it means. You don't know which order it is. So the way we have a cheat system. O, B, A, F, G, K, M. Anybody know what that means? Okay. O, B, A, fine girl, kiss me. That's the way we remember it. O, B, or if you're a girl, you might say, O, B, A, fine guy, kiss me. Or you can do it the other way. How you want it. Anyway, that's how you can keep the order of the spectral classification. Galaxies have all different shapes. Okay? We think up till now, we thought we've had a spiral galaxy like this or that. Now we're getting some data that may indicate that we're actually a barred spiral galaxy like that.
Change that. So there's more there.
Well, it's just the shape of it. Anyway, there's galaxies that are just long streaks. There's these really irregular galaxies. These, all different shapes. By the way, here's some more of these abbreviations. That's New General Catalog, NGC. M is a Messier. We'll talk about what this means in a minute. Different ways.
I got a question about this. It's impossible. So I'm curious about how about 100 billion being known. A human brain can't know 100 billion. So is this like the computers that store the images? know that there's 100 billion out there?
Well, it's that's how many have been. What it doesn't necessarily mean they've counted them all, but if they count an area of the sky that looks a certain way, you could multiply that times the rest of the areas that would represent and get a rough estimate by doing that. And the bigger area that you count, the more accurate all that becomes. So that's one thing you can do. But there are actually people that actually count these things as years and years and years and years and long projects. So, but the accuracy of that, I don't know about that.
All those 100 billion don't have designations, do they?
Every one that we know about generally do. I mean, I'll show you in a minute the designation. Okay, nebula, and I'm sure you've heard of nebula. The word nebula is an old astronomical term. It just means nebulous. It was unclear. It was fuzzy. That's where the nebula came from, was that word. And of course, early in the game, there was a whole lot of nebula. There'd just be this fuzzy object, either because of the quality of the telescope or some other factor that made it fuzzy. And over the years, a lot of those have been found out to be other things besides fuzzy objects. We still have nebula that are still fuzzy objects. But most of the truly fuzzy objects are clouds of material, like I told you about a sun blowing up. That would produce a cloud of material from its destruction that would be fuzzy. It would be a nebula. Those are going to stay nebulous. But the ones that were because of some technical thing where we really couldn't see it clearly, we're picking away at those. So here's just some of them. Constellations. Now, constellations are kind of interesting. We use them all the time. Astronomers use them all the time to locate in the sky groups of stars. So it kind of we can focus on that area when somebody says it's in a constellation, rather than looking all over the sky. It just serves as a kind of a roadmap for us. But again, these were named by different civilizations over different times and different objects and different combinations of stars. For example, Cygnus the Swan. Now, obviously those shadows weren't there. Those have been artificially placed there. But they pictured this group of stars as representing a swan. And they named it Cygnus the Swan. Or it could be the little bear is the Little Dipper. Ursa Minor. Ursa Minor. And the big bear is Ursa Major, is the Big Dipper. And Ophiuchus is this. That's a serpent bear. That doesn't show us very well. But the pictures you see of that would be this guy wrestling with the snake. So that's the snake over here. And this over here is Virgo the Maiden. We use this constellation here so much to line up our telescopes that I went ahead and just named it for you. See that little thing looks like a kite? And that star right there is in that constellation. That's Arcturus. Arcturus is really bright and it's really easy to find. So, when we line up our telescopes for the computer to be able to line up what we want to see, we have to calibrate it to start with on some known object. So we often use that. Although there's other, and that means that's Boides is the whole name of that. It means the cloud. So these constellations are just arbitrary shapes that we've looked at in the sky, and we still use them. Those, that's an example of how many's up there. You see what's above you along your own latitude. Anybody know the latitude? Yeah, it's a little over 37. If my telescope in Fayetteville is 38.06. The latitude is. So And of course, if you're up or down on your latitude, you're going to get a different set of constellations that we're talking about. The constellation stars are designated by their brightness. All the stars within a constellation have a relative brightness to the rest of the stars. So the brightest star is the alpha star. Just like we talked about a while ago with Orion, the alpha star is what? Betelgeuse, the brightest star. The second brightest star is Rigel, which is this, the other corner down here. So it's the beta, and alpha, beta, gamma, delta. Right down the this is the Big Dipper. They just go right in order along the Big Dipper, which is just kind of a coincidence more than anything else. But the front one is alpha, beta, gamma, delta. But that's not because they're in order. That's just because they happen. The brightness happens to fall that way. So we talk about the alpha star, the beta star, but that just to kind of give us some, again, the directions that we can talk to each other about. Other things you can see in the sky are meteors and comets. Meteors and comets always have two main trails behind it. It has the trail that's following the comet. A comet is nothing but a dirty, we call it a dirty snowball. It's ice and, some dirt. It's this debris that's collected and frozen. And so as it goes through the sky, it leaves this trail behind it where this ice is melting and putting this vapor trail behind it. And of course, the closer it gets to the sun, the more the ice melts, so the more vapor there is. But there's also this other tail that goes opposite the sun. So wherever it is in relationship to the sun, there's going to be this second tail that is the sun's rays pushing that tail out to sea level. So that's one of the ways you can tell if it's a comet. A meteor is one rock or one something coming through the atmosphere, burning up in the atmosphere. It usually, a meteor is just a big rock. Maybe it could be something that's been floating around in our solar system for millions of years and just finally, by coincidence, crossed our paths and went through our atmosphere. A lot of them are from that meteor belt. It goes, or asteroid belt that goes between Mars and Jupiter. That meteor, by the way, I keep talking about that asteroid belt. That asteroid belt is maybe a failed planet that blew up. It may have had a big crash with another failed planet, and they crashed together and just blew up and distributed that rock all the way around that orbit, and it's still floating around. There are thousands of meteors. But the total volume of all those rocks put together is not very much. But the trouble is, it can be very destructive. If one of those big ones should be kicked out, because they're flipping around all the time. They're hitting each other and bouncing. And if one would be kicked out of orbit and come our way and hit our Earth, we'd be in deep doo-doo just like the dinosaurs. That's what killed them. It's one of those dudes hit the Earth. That's another controversial theory. Tune in 1,000 years from now, I'll give you their theory then.
Yes.
All kinds of theories about what really killed the dinosaurs. That's just one, but it's the most accepted theory. So the other thing are these meteor showers that we get. Now, when you have a meteor shower, it's because at that point, the Earth is going through the tail of a previous comet that has gone through our area. So as the Earth rotates around the sun, if it goes through where a comet has been, there's still debris flowing back, and that all comes through our atmosphere and burns up in our atmosphere, and you see them as these meteor showers. I understand that? Okay.
I've got a question about the comet. When you said ice and dirt, does ice necessarily mean H2O or could be other kind of ice?
Well, here it does, but there are ices of other things.
But a comet's ice is H2O.
In fact, one of the theories about where we got our water on Earth was from comets crashing into our planet and providing the water that we have. It is water.
Okay.
The Perseids, there's the Swift, was the Swift-Tuttle comet. You can tell each one. That was last seen in 1862, but it has a 132-year-old period. So what does that mean? Actually, the last time it was seen was in 1994. So we actually saw that comet go by. And these are all the meteor showers and where they came from this year. And that's pretty much repeated every year. And these names are the names of the meteor that it's coming. So you'll see those announced on TV and on the radio. Perseids are coming, the Indians are coming. You know, everybody calls me and wants to come look through my telescope to see them. And of course, you know, that's the worst place to look at meteor showers through a telescope because you can't see anything. And yet you got to look up at the sky. You can also see airplanes, okay? Now an airplane, this is a repeated exposure. What they're doing here is they've just opened the shutter and left it open till that plane flew by. So that's a lot of exposure. Actually what you see is this spot of light going through the sky, really. And you can see it move. And often airplanes have flashing lights on them, so you can also see the flashing lights. But all of y'all have seen them at night. This is another airplane. This is the airplane one. This is a satellite. Same thing. Satellite goes through the sky. You see this moving point of light without a flashing light with it, like an airplane. It's real tiny, and you just see it moving through the star. It could be a satellite, or it could be a space station. Now, the space station has been. This is a. If you look, every one of those sets of stars, they're double. So what they did is hold it open for 2 revolutions around over the sky. So that, but they're never a continuous line. It's a spot. Y'all do understand. So these are just some terms in the way you look at the way we talk about where things are above the Earth. The ecliptic is the angle at which, the line at which all the planets are revolving around the sun. It's in a plane. They're not randomly distributed. We're in a flat plane of planets. All those planets are in like a plate. You take a dinner plate and you just line them up across that plate. That's the way it would be, and they all turn independently. So that's why you get different planets in the sky at different times, because some go around the sun faster than others. So sometimes you see 2 together, sometimes you see 1, sometimes you don't see any, but you always see them around the ecliptic, and the ecliptic is at 23.5 degrees and from the pole of the Earth. The Earth is tilted against that rotation around the sun. Of course, you know about our equinoxes when it crosses at the time of the year that the ecliptic, where the ecliptic is at the celestial equator. That's when the night and daylight and darkness is the same. So we have 2 of those, and then the summer and winter solstice is when they're the extreme, the other one. Obviously, the southern hemisphere is looking in a whole different direction. They're on the bottom of the ball looking out that way. We're on the top of the ball looking out this way. So, you know, they see a whole different set of stars, everything than we do. Y'all do those things. Also in the ecliptic, there's these specific constellations overhead every month. just because of the rotation of the Earth against the sky. And of course, the idea of astrology is that whatever month you were born under a certain constellation. And as a result of that, your life would be altered in some way. You'd have a different personality, or you'd be cuter, or dumber, or smarter. If you believe in all that nonsense, that's what that came from. And it's nonsense, but it's still in the newspapers. You can still look up your sign, see what's going to happen to you that day, because you're born in June. I still have people introduce me to speak as
Oh,
the
no.
local astrologer. It's just a term that's so common, it just comes out. They know that. Then here's the ecliptic I'm talking about again. See, they're all lined up in this flat area. And so when you're looking up at the sky, you're looking at this path that all those planets will always be in front of you. Now there's coordinates in the called celestial coordinates. Declination is what we call the same thing as latitude. But from an astronomical aspect, we call it declination. Declination is from the celestial equator up, and it's in degrees, just like latitude. Right ascension is the same as longitude, but it is, you know, our reference point for our longitude is what? Greenwich. Greenwich in London. You know, every country wanted to be the center of the Earth for many years, and they finally agreed that they would just pick one. But Aries is the reference point for right ascension, and it's measured in degrees, just like longitude. That way you can center things, and a lot of telescopes you can set up your telescope with declination and right ascension as your coordinates, just so you can type that into your telescope and it'll go to that point. A couple of terms that you might hear, of course, these are common terms with zenith, of course, is what's straight over your head. Nadir is what's down below your feet, even if it's on the other side of the Earth. Astronomical horizon is straight out from where you're standing, and the true horizon is along the edge of the Earth where you're standing. By the way, sidereal time, if you ever hear that term, is used in navigation, but instead of using the right ascension, they actually go the opposite way on there. So their sidereal time that they use for calculation to navigate, they don't do that anymore. Nobody does anything. Nobody even knows what a sextant is anymore. But back when they did it that way, they had to know all that to calculate. Now let's get back to some of these references. There's a lot of these M objects. That's Messier objects. In 1771, Charles Messier listed all these fuzzy objects in the sky. He had 101 of them that he didn't know what they were, or 110 of them. They didn't know what they were just fuzzy objects. Now a lot of those become designated as some of them are actually ended up being galaxies. M42, for example, that is M42. That's the M42 is the Orion galaxy. If you take the belt of Orion and look just below it, supposedly a sword hanging down right in the middle of it is this reddish area called the Orion Nebula. That's one of those exploded planets, and it's we can actually see by the Hubble telescope, it's starting to get organized to build. It's making a solar system in that nebula. You can actually see what we call protoplanets, which are the beginnings of the planets going around centers. body of the sun. Okay. The new general catalog, usually called NGC catalog, the first time it was compiled in 1888 by Ryan Herschel, they had 7,840 objects in it. That's grown now to 13,993 objects. You can look these up in all kinds of forms. You can look. This came off the internet. I just looked it up, and you can look up. You can type in a number, or you can type in a common name and get its NGC designation. It'll even give you a kind of a rough picture of it. I've got books at home that are this thick. They're just full of these, this page after page after page, these numbers and designations, so you can kind of see what you're looking at. There's apps you can get. They're just endless what you can get. My recommendation is, I would try if you really want to download something, it's free, Star Walk 2. You can download it on your cell phone. I've got it on mine. So I can turn my cell phone, I can punch that app, and I can hold it there for a second, and it'll tell me exactly what's in the sky above it. It'll show me. I could do it right now, even when the clouds are there, and it would tell me what was there if it were clear. So if you're out looking at something and you don't know what's there, you can turn that on, look at it, you know what's there. Okay. This Star Walk 2 is another computer program that you can put in the date and your coordinates on the Earth, like your latitude and your longitude, GPS coordinates, the date and the hour, and it'll tell you what's in the sky at that moment. If you want to know what's going to be in the sky at 7 o'clock in 2016 in Pipestem, you can type all that in, and it'll show you the sky at that moment. And what's that? Really, it's a really cool thing. So, if you'll, the program that I've used for years is Starry Night Pro. That's a computer program. It's a lot more sophisticated. You can hook this to your computer and drive your computer with the coordinates off of it. I mean, your telescope. But it did a lot of the same things for years for me that these two things do now. So much easier. It's all free. That's not free, but these are. So this is a sky chart that typically we used to have in the past. And the whole idea of these sky charts are nightmares. I mean, they sold these things everywhere. And the whole idea is you look at that sky chart and you try to pick out something that you can identify up there as a reference point. You turn this thing around till you get those lined up with what you can see, and then you can see where the other things are if they are. That's this. Well, I never could do that very well. Have you ever used one of them?
Yeah, nightmare.
It's awful. You know, they should be against the law. So all they do is drive you crazy. I think that truck might be using one of those. I shouldn't say. All right, now this is another thing. If people have this idea that if they get this telescope, they can look up in the sky and see everything. And you can see a lot. They're fun. But this is what people, when they look up there, they're expecting to see that when they look at Mars. Now, through my 14-inch telescope, that's what you see. And that's a big telescope. Same thing with Saturn. Saturn is, that's what you expect to see. And that's what you see with a 14-inch. Now, you can actually see that same image very well with a pair of binoculars. It's not quite that big, but you can see it clearly. You can see the ring. Jupiter, same thing. Now, if you look very closely, you have to really look close, but you can see the four moons are at it. With binoculars, they're even more. The moon, people think, can you actually see the rover that left there? And see the tracks. Well, No. You can see that. It's really interesting. And the Orion Nebula we talked about, here's Orion, here's that nebula right there. That's what people expect to see, that's what Hubble sees, but you're not going to see it. So bottom line is, astronomy is really, really interesting. I think that's universally kind of accepted. But by far, the best part of astronomy is learning about it, not the gadgets. People go for the gadgets every time. Get a books and study, and then you can kind of progress however you want to progress along, however far you want to go into it. Use your binoculars to start with. The worst thing you can do is to go out and buy a cheap telescope. This is a classic. I don't know who left this. I think they must have heard me. But this is an old Bushnell that you used to be able to buy at Sears or Memory World. These things are absolutely. If you ever hated astronomy, you're going to hate it after using that, because you can't keep it lined up. It doesn't focus well. You just wrestle at that thing until you're just sick of it. You throw it down and say, "The hell's astronomy." Okay? Especially kids. Kids, you know, they want a lot of feedback that's positive. They don't want to have to wrestle around with some cheap thing like that that discourages them, and that really discourages them. And I have a whole lot of parents who go to these star parties for the schools and stuff like that, and the first thing parents run up and say, "What kind of telescope should I buy?" What? They just, that minute started getting their kids interested in astronomy. I said, why don't you hold off on that for a little while? Go through to them learning about it. Another good thing to do is join an astronomy club. We don't have a lot of astronomy clubs. I belong to every one in West Virginia. I'm in the West Virginia University Astronomy Club. I belong to Kanawha Valley Astronomy Club in Charleston. We have our telescope at Camp Virgil Tate for all of you might know that. We have another one in Clarksburg, another astronomy club there. None of them are really very active. But if you can join an astronomy club and associate with people that do this a good deal. There's a new program starting at the planetarium in Charleston, at the Clay Center, that they're promoting astronomy. It's essentially free. I think they're charging $10, but they don't even care to pay it. They even give you popcorn. It's once a month. You can look at their website if you're in Charleston area. Make sure you have to do that. All of those kinds of things that you can do to kind of just do the same thing we've done tonight, but you do this over and over and over until it becomes just second nature. This star chart that I gave you was off of that website. It shows you, I did it for the 7th last night at 8:30, 9:30. And I did that. I had to send these to get them printed when we sent those in a month ago. I just looked up this date, put in that time, it printed out. Right now, if you can see out there, that's these purple things didn't show up very good. But this is Mars, the moon was right there, and Jupiter's up there. We can see that. Our longitude right here at this point is 37.533. That's how accurate you need to put these things in. So, I have a whole bunch, not a whole bunch, I just, like I told you, I bought a few things you're welcome to come up and look at. Some people will just take their cell phone and take a picture. The two books that I recommend are the ones by David Levy. David Levy was the Levy that was on Shoemaker-Levy Comet Collision. You remember that? This is that guy. I knew him. He's a really nice guy. He's dead now, but he made these books he wrote these books for people starting. These are the two magazines that are common for astronomers. I get both of them. They're not very expensive. They've got a lot of information. You get one a month. You can read a lot about astronomy. In the center, that shows the map, the same map that I showed you a while ago. It even shows you the position of all the moons of Jupiter and where they are every month. And if you look on page 79 of Sky and Telescope, there's an ash dome advertisement. It shows my dome. They use my dome as their advertisement. After all, I paid them this year. But anyway, most people get one or the other. You don't need to get them both, but if you're really into what you want. But they also show all the equipment. This is a great book. It's cheap. I don't know if you all know about these DK books, but they're wonderful. There's a whole series of books, and they're all this size and this thickness on different topics. I've got about 8 of them now. There's one on paleontology, there's one on geology, there's one on science, and there's the one on the universe. These, just look them up on Amazon.com, or just look them up, and they're like $20, and they're just absolutely wonderful books.
You call them DK books?
Well, DK's the company that puts them out. A lot of them are through the Smithsonian. This is a book that you can actually download online. You just go in, look up this book, Astronomy, and you can put your printer to work and print it down for free. Or you can buy it. So I bought it. But this is, I just brought the book just to show you. You probably don't want to start with that book. And then Messier album, that shows you all those Messier objects and what they were. These are just getting a little more specialized. Here's another beginner book. Here's one of those Audubon books, they do everything, even mosses and ferns. But those might be some good books on it. If you insist, if you just absolutely have to have it, just because you want to buy a gadget, I would suggest that if you ought to do a lot of research on telescopes before you buy it, but I would suggest you buy Celestron Next Star. And you can either get a reflecting telescope, a Newtonian reflector, which has a mirror in the bottom, or you can get the refractor, which is one of the typical one you look straight through. You can get, they both have motors on them that drives them to keep them even with what you're looking at, and they have computers in them that you can calibrate, just like I've been talking about, and you can track. You can say, you just type into the thing what you want to look at, and it just goes to it once you get it set up. And those will cost $300 or $400 or $500. But that's where you ought to start. There's another lecture I could give, but I'm sure y'all are sick of astronomy right now, but anybody that wants to hear it,
What's it about?
what?
What's it about?
It's more specifically what we've talked about, but I go into a lot more detail about the planets and different things. Any questions?
Should we be writing into our senators and this about Elon Musk and SpaceX putting up 3,000 bright satellites in the sky?
Yeah, I don't know. It's just like we're so spoiled now with gadgets and data and what we do with it. I don't know. We're really loading up our sky with junk, and we've got satellites up there that have already gone out. It's just trash going around, and we're going to get to the point where we can't get anything in the sky because we'll be running into all the trash, and plus it's all going to come crashing down on us. Those are finally, all those objects lose their gravity because they start dropping. So I don't know where the limit. It's not one of those what the hell are we doing to ourselves questions with our environment and our sky. Light pollution is my big thing. I fight light pollution. We had a new shopping center go up in our area, and when they were designing it, I went down. Fortunately, I was on another committee for that, and I was able to get to the people in charge and have them change the lighting to the dark skies lighting that shines down instead of out. These damn sodium lights, and I got them all up and down my street. I talked the guy, the first guy that came to replace the bulb, into not connecting it. And I got away with that for 4 or 5 years because the way they patrolled the neighborhood was to tie ribbons around the telephone poles when the lights are out at night. The policemen would. And I knew that. So when I saw one of them, I'd rip it off the pole so they wouldn't know that it was out. But they finally caught on to my game, replaced it. The last time I couldn't prevent it. Here's this thing right almost in front of my eye.
Oh.
The sodium lights, the light spectrum is just the worst. But all this stuff, I don't know. You know, I feel like John Cutie. Sometimes I'm mad all the time about what we're doing to ourselves and our planet. To me, so it's quite time for me to die.
Is that a yes?
I had read they had 3,000 satellites going up in the
Yeah, well, I don't know if it'll be 3,000, but his idea is to. But the information that they'll provide, as soon as people understand what that'll do for them, they're going to like it. They're not going to understand the consequences. We don't understand the consequences of using plastic bags out of Kroger's. I mean, look at this stuff that we do every day. You and I, who are the ones that are the conscientious ones, look at what we do every day. Us. That is just absolutely unacceptable. So, I understand, I agree with your point, but I don't think we can
One other related thing, Spruce Knob has some of the darkest skies in the east, and over Labor Day there's the Almost Heaven Star Party, which I haven't been to yet, but want to go to. It's supposed to be absolutely phenomenal, put on by I think the Northern Virginia Astronomy Club. So if you really like astronomy after his talk, check out their webpage.
We also have the Kanawha Valley Astronomical Society always puts on every year at Blackwater Falls a astronomy weekend with.
Oh, that's you guys. Okay.
And so, you know, if you just look up Kanawha Valley Astronomical Society, you know, give you the details about. We stayed at the lodge. And we have all of us are getting smaller and smaller, but we bring our telescopes and set them up, and you know, we show everybody can see through them. And we have lectures all day long on astronomy.
When is
Up
that?
there
It'll be in September. I don't remember the date. What?
up there in Spruce Knob, what she was talking
Now,
about.
Spruce Knob's not the one we do. We
Right,
do it Blackwater.
I know, but at Spruce Knob, they have a little sky observatory building, and there's a guy from that club, that Northern Virginia club, that comes out every month on the new moon,
Right.
and he has a big telescope inside this building, and he takes pictures of some of those fuzzy objects, the Messier objects, through this big scope.
I want to say how wonderful KVAS is for their Blackwater thing. We took Master Naturalist there, God, what, 10 years ago? Fascinating. Just the lecture, to me, the lectures were, because they talked about.
Well, we usually have a guest lecturer from JPL who talks about whatever they're working on JPL, but then we also have telescope lectures.
They talked about the successor to the Hubble. I could never remember the name of it. It hasn't gone up yet.
That's the JPL.
Okay, the name of the, I forget the name
I'm
of the telescope.
struggling to think of myself. It's a common name. It's a guy's name.
Yeah, it was so interesting.
Yeah, and it's going to be better than Hubble.
Huh?
If
No.
I know y'all want to go, so if you want to go, go. If you want to ask questions, I'll stay here all night. If you want to see more stuff. I'll leave these books up here if y'all want to go through them and take pictures.